Okay, friends, welcome to Macros tutorial section, and we are going to do econometry second 444, and our main target for today is heteroscedasticity. But before then, if you are watching this video, I would like you to subscribe to this channel and share, so that anytime we post a video, you'll be able to have access to it easily. So let's get to our objective. We should be able to perform a Spearman rank correlation test at the end of this tutorial, and each and everyone watching this video should be able to detect the existence of heteroscedasticity using t-test. Now friends, before then, let's try and define some things here. Heteroscedasticity. Heteroscedasticity is said to have occurred when the variance of the error term is not constant. Okay, so it means that the variance of the error term is supposed to vary. But before then, I want us to remind ourselves of certain things here. So now let's do some recap here. So we all can recall, under the assumptions of the OLS, that the expected value of the error term here is equal to 0. Okay, so it means that when we want to compute the variance of the error term, that is variance of ui, we are supposed to get expectation of ui squared minus expectation of ui all squared. So, but since we have the expectation of ui here to be equal to 0, so it's in effect we have the variance of the error term, that's v of ui, to be equal to expectation of ui squared. Okay, so it means that the variance of ui is supposed to be equal to expectation of ui squared, which is equal to sigma I squared, which is not equal to sigma squared. So this is what the slide or the presentation is trying to show here, that whenever we have the variance of the error term not constant, that's the variance of ui being equal to sigma I squared, but then the variance of ui here is equal to sigma ui squared because of this assumption holding. Okay, so anytime we have the variance of ui here to be equal to sigma I squared, it means that heteroscedasticity exists, in that I, it is as a result of I varies, because of this I, we can have variance of ui here to be equal to sigma 1 squared, sigma 2 squared, and so on and so forth. So let's get back to our slide. So heteroscedasticity. So as we have said earlier, that we can see heteroscedasticity as occurred when there is no constant variance in the disturbance term. So when we have the variance, as we have showed earlier, the variance of ui to be equal to expectation of ui squared to be equal to delta I squared, which is not equal to sigma squared. So when this scenario holds, then heteroscedasticity exists. Now, homoscedasticity is said to have occurred when there is this constant variance in the error term. Okay, so now, in other words, the variance of the disturbance term does not vary. Okay, so in effect, we have variance of ui to be equal to just delta. We don't have any I here, so it shows that the variance of this ui, the disturbance term here, does not vary. So let's continue. Our interest is not on homoscedasticity, our interest is heteroscedasticity. So we are going to pay much attention to heteroscedasticity. So now, if the OLS assumption that the variance of the error term is constant for all observations does not hold, we face the problem of heteroscedasticity. Yes, it's true. So under the OLS, we have several assumptions. For example, we have, as we have stated earlier, the expected value of the error term supposed to be equal to 0. There should be linearity in the parameters. Okay, and as we have stated, the variance of the error term is supposed to be constant. So now, when we have the variance of the error term here to vary, okay, when we have the variance of the error term to vary, then it means that heteroscedasticity exists. Okay, so that's it. So now, let's look at some of the effects of heteroscedasticity here. Now, heteroscedasticity may lead to unbiased but inefficient estimate of the coefficient. Yes, it's good to get an unbiased estimate, but then because of the inefficiency is as a result of the large variance. Okay, so when the variance
of the error term is large, okay, then it means that it can affect the precision level, okay. So when we are performing a regression analysis or a regression model, our main objective is to make accurate precisions, okay. So when the variance of the error term is large, it affects the precision level, so it's also an effect or a negative effect of it. Now another effect is that heteroscedasticity may lead to biased estimate of the standard error, that is incorrect statistical tests and confidence intervals. Let's continue. So let's try and look at the statistical or mathematical definition of heteroscedasticity. So now, as we have seen earlier, that the variance of ui is supposed to be equal to expectation of ui squared, which is supposed to be equal to sigma I squared, which is not supposed to be equal to sigma squared. So we all know that heteroscedasticity can be defined as this. So when this scenario holds, then we can see that heteroscedasticity exists. So now let's look at a simple linear regression model where we have y to be equal to beta 1 plus beta 2 s plus ui. So we can recall that when we want to estimate our beta 2, I agree. So beta 2 here will be equal to summation of xy on summation of s squared. So when we denote sigma x or summation of x on summation of s squared, when we denote this with k, we end up getting beta 2 cap to be equal to summation of kiy. So we denoted this sigma x on sigma s squared by summation of ki. So when we represent or denote, we end up getting this. Now we substitute this y here. So when we substitute the y here, we end up getting summation of k into bracket beta 1 plus beta 2x plus mu I. But then we all can recall that that's last semester, that summation of ki is equal to 0, and when we sum ki si, we are supposed to get what? 1. Okay, so we should recall that. So now we are going to expand it. So when we expand summation of ki, so when we are expanding, we are going to multiply through by summation of ki. So summation of ki times beta 1, we will get beta 1 summation of ki. But then knowing that summation of ki is equal to 0, then it means that when we multiply beta 1 by summation of ki, everything will result to 0. So this one goes off. So now let's continue. When I multiply summation of ki by beta 2x here, I'll end up getting beta 2 summation of kix. And as we know that summation of kix here is equal to 1, when I multiply beta 2 by 1 here, I'm going to get beta 2, and this is what we have here. Okay, so now summation of ki times mu or ui is going to give me summation of ki ui. This is what we have here. So now this is our beta 2 now. Good. So now when we find expected value of this here, we know that we are going to get unbiased estimator here. So if it's unbiased, expectation of beta 2 is supposed to give us beta 2. So expectation of beta 2 is supposed to give us beta 2. So now let's continue. So our interest is to find the variance, and as we have stated here that the variance of the error term here is supposed to give us expectation of ui squared. So the same way, the variance of beta 2 cap here should not be different from expectation of beta 2 cap minus beta 2, because we know that when we want to estimate for the error term, that's expectation of ui squared here, we are supposed to get beta 2 cap, that's the estimate minus the parameter. Okay, so what you have estimated and what you are estimating, so that's it. So we are going to get expectation of beta 2 cap minus beta 2, so that will give us that. Okay, and we know that it's supposed to give us expectation of ui squared, so the same thing. So variance of the error term here is going to give us what? 0. Sorry, variance of a constant is equal to 0, but expectation of a constant is the constant. So when you find the variance of beta 2, you are going to get 0. So variance of beta 2 here is just going to give us the expectation of this because of this assumption holding. So this is what we are going to get. Okay. So now we know. So now let's run the expectation through. So when I run the expectation through here, I'm going to get summation of ki squared because the square will affect this and that. I'll get summation of ki squared, expectation of ui squared. But what is expectation of ui squared? Expectation of ui squared is equal to sigma squared. So in the nutshell, variance of beta 2 here will give us this summation of ki squared, sigma I squared. So now when we substitute ki, so now we represented ki to be summation of s on summation of s squared. Now, so it means that our ki squared will give us summation of si squared on summation of xi all squared, then multiplied by sigma I squared. So because of this, we say heteroscedasticity what exists because the variance of the error term would vary. Now for homoscedasticity, this is what we are supposed to get. So let's continue. So let's look at some of the consequences of heteroscedasticity. So we stated this already that OLS estimators are still linear and unbiased. Yeah, we said this one earlier on. Variance of beta i's, that's beta cap i's, are not minimum. Yes, so it means that at this case, the error term, the variance of beta i's, the estimators here are very large. So it will affect the precision level, and we have the variance of beta cap to be equal to this instead of that. You know, so this is heteroscedastic and this is homoscedastic. So now we have bias standard errors or variances. So that's it, as you can see here. And we have T and F statistic unreliable. Yes, we know. So now, because this is because the error term here cannot be minimum. Okay, yeah. So now, as we stated in the objective, let's go to the objective, the main objective. So we said that the main objectives for this tutorial session is to perform a Spearman rank correlation and to be able to detect the existence of heteroscedasticity using t-test. So now, that's our main objective. So now let's go to our main objective here, Spearman rank correlation. So what does it aim to achieve? So the Spearman rank correlation test assumes, so this is an assumption, assumes that the variance of the disturbance term is either increasing or decreasing. Sorry, increasing or decreasing, yes. So as x increases, therefore there will be a correlation between the absolute size of the residuals and the size of x in OLS regression. The data on x in the absolute values of the residuals are both ranked, and the rank correlation coefficient is found. So yes, as by the name Spearman rank, we are supposed to rank. Another to add up the Spearman rank correlation will try to look at whether there exists a correlation between two variables given x or y. Alright, okay. So it compares two variables. Good. So now let's look at the steps. First step, we have to fit the regression to the data x and y. So as I stated earlier, it looks at for whether there is a correlation between two variables. So now we have to compute or find the error term, estimate for the error term. But then after estimate, you have to ignore the signs. You have to just take the absolute values. Now back to the objective, we said we should be able to detect heteroscedasticity using a t-test. Okay, so now the only time we can perform a t-test is when the row or the sample size n is greater than it. So when you are with a given sample size and the n is greater than it, we can use the t-test too. So now let's consider the t-test here. So for Spearman's rank correlation, we are not comparing means, so the t-test that we use here will not be the same as the normal t-test that we know. Okay, that we are not comparing means. So this is the t-test for the Spearman rank correlation. So for the Spearman rank correlation, the t-test here is going to give us RS multiplied by root on n minus 2 all on 1 minus rs squared, where the rs here is our Spearman rank correlation, and this is how we compute for our Spearman rank correlation. So our rs here is going to be 1 minus s summation of di squared on n squared minus 1. So now, with our model given earlier, with this model we have two parameters, that's beta 1 and beta 2. So we have a degree of freedom of n minus 2. So where we have more than two parameters, it will be assuming three parameters, n minus 3, and so on and so forth. Okay, so now this is our hypothesis, the null hypothesis. H naught is said that rs, where rs is our Spearman rank correlation, so our rs is equal to 0. That means, or in other words, you can see that H naught is said that homoscedasticity exists. So our null hypothesis will be in a way that H1 is said that there is no homoscedasticity. Okay, or H1 is said that rs is not equal to 0. So that's that. So now let's take a simple example and let's run through it, and we'll bring this lecture or tutorial to an end. Okay, so now with this data given, or with this data given, this example given, we are going to concentrate or pay much attention to the question C, where it says that we should test homoscedasticity using Spearman rank correlation. Okay, so now with the same data we rearrange them. So this is what I did here. So with the same data, I have my country, I've written them vertically, and my y. So my y here, I values, is what I've written here. And mind you, we are doing Spearman rank correlation, so I have to rank my y. So this is how we do the ranking. So now for the ranking, depends on the one doing the test. So now for the ranking, what we are going to do is that, for me, I denoted my least value with 1 and my highest value with what, 10. So another person can decide to denote how do you call it, the least value with 10 and the highest value with 1. So rank means you are ranking from highest to lowest. So that one, it depends on you. So that's what I did. So now for my y, I had my least value to be 0.2 and I ranked it with 1. Okay, then my highest value to be 102.0 and I denoted it with what, 10. And my second least value was 0.8 and I represented it with 2, in that order. So you have to rank them. Then I'll come to S1I. So these values, I rewrote everything here vertically and I ranked them. So I had my least value to be 2.3 and I ranked it to be 1, and my highest value to be 543.1 and that I ranked it to be 10. Then my x2i2, same thing, I rewrote everything and I ranked it. My least was 0.8 to be 1, my highest is 743.2, that one to be 10. Now let's get back to the slide. So now this RT test, that's RS, so it means you have to compute for RS here, and this is the formula how to compute for RS, which is giving us RS to be equal to 1 minus 6 summation of di on n squared minus 1. But the di here is the difference in the ranks. So now we are done with our ranking, and as I said, Spearman rank correlation looks at two variables, but then in this example here we have three variables. You have the dependent variable, one dependent variable, and you have two independent variables. So we have yi to be the dependent variable, and we have x1 and x2 to be how do you call it, the independent variables. Okay, so in this case we have three parameters, so our degree of freedom here is going to be n minus 3. So should have it at the back of our mind here. Okay, so let's continue here. Sorry. So now D1 is my first rank, so that one I'll find the rank of yi. So I'll find the difference between rank of yi and rank of x1i. So that's the difference. So rank of yi, the first one is 1 minus 1, give me 0, 10 minus 10 here, 1 minus 1 gave me 0, 10 minus 1 gave me 1, 4 minus 3 gave me 1, 8 minus 8 gave me 0, 7 minus 5 gave me 2, then 5 minus 6 gave me negative 1, 2 minus 2 0, 6 minus 7 6 minus 7 negative 1, 3 minus 4 negative 1, 9 minus 10 also negative 1. So this is my D1, which records or denotes the difference in the ranks of y1 and x1i. So we do the same thing for yi and x2i. That will give me D2. So when I find the difference between ryi and x2i, I'm going to get D2. So that one too is going to give me, so rank of y, the first one, 1 minus 1 giving me 0, 10 minus 10 giving me 0, 4 minus 4 giving me 0, 8 minus 8 giving me 0, then 7 minus 7 also giving me 0, then I have 5 minus 6 giving me negative 1, 2 minus 2 giving me 0, 6 minus 5 giving me 1, 3 minus 3 0, 9 minus 1 9, so also 0. So that's that. So I've performed my rank. So now we go back to the formula. So in order to get our t-test, we have to get our RS. So this is our RS, so it means we have to get DI, and we found our DI. So it means that our RS1 here is going to give us 1 minus 6 summation of D1 squared, all on n squared minus 1. So this is that. So this is our RS1. 1 minus summation of D1, sorry for the handwriting, 1 minus 6 summation of D1 n squared minus 1. So now our n here is 10. So as we can see, 1 2 3 4 5 6 7 8 9 10. So the sample size here is 10. Good. So now, and my summation of di squared, so this is it. So that's d1 squared. That will give you 0 squared plus 1 squared plus 1 squared up to negative plus negative 1 squared. So I'll square these values and sum them, and when I do that I end up getting 10. So you can try that. Probably my computation might be wrong, so you can try that. All on n, where n is 10 squared will give me 100 minus 1. So after inputting computing, I had my RS to be equal to 0.940, and my T1. So with this formula, it helped me to calculate for my D1. So my T1 was given as RS on times root of n minus 2 on root of 1 minus RS squared. So this is that. So my RS1 is 0.940. This is it. N is 10 minus 2 on square root on 1 minus 0. That's RS1 squared. So this is that, and I end up getting this. So we do the same thing too for RS2. So with the formula, RS2 will be giving us 1 minus 6 summation of D2 squared n times n squared minus 1. So I have my RS2 to be equal to 1 minus summation of D2. So I'll square these values and sum them. So when I do that, I end up getting my D2 summation of D2 squared to be equal to 2. So when I do everything, my simplification, I end up getting my RS2 to be equal to 0.988. Okay, and when I perform my t-test using the formula given, I end up getting this. So we've been able to compute the t-test. So now, sorry, we didn't state the hypothesis, but then I stated them earlier. I should have started with the hypothesis. Sorry for that. But then I stated them that when you are computing, the hypothesis is supposed to be, H1 is supposed to be that there is this homoscedasticity, or RS should be equal to 0, or and the H1, that's the alternate hypothesis, said that there is this heteroscedasticity, that's RS is not equal to 0. So that's our hypothesis. Now after getting our t-test, what we are supposed to do is that's our t calculator. We have to find our t critical. So that one we read from our table. So assuming we have our alpha, or our significance level of significance, to be equal to 0.5, So now we are estimating for three parameters: beta 1, beta 2, and beta. That's from the question. We have this. So this is the question. We have x1 and x2. So it means we are estimating for three parameters: beta 1, beta 2, and beta 3. So our degree of freedom is supposed to be given as n minus 3. So we are going to read T alpha for the first one here. For the first one, we are going to read T alpha, which is 0.05. Sorry, I didn't bring that. To read T1 to be T alpha 0.05 n minus 3 for the first one. So T 0.05 n minus 3. So this is our level of significance. N minus 3, n is 10, minus 3 will give us 7. So I'm going to read 0.05 and 7. So this is what I'll get, 1.89. Okay, and obviously when we come here, we can see that our t here we had 7.793. Okay, so our t calculated here is greater than our t critical. So what do? We reject. So when we reject our null hypothesis, then what is it trying to say? There is this heteroscedasticity. It means that homoscedasticity does not exist here. Likewise, we do for T2. Obviously, we can see for T2 we have 18.093, which is obviously greater than 1.89. Yeah, so that one to reject the null hypothesis. So in this case, it's heteroscedastic. So that's that. This is how you use Spearman rank correlation t-test to detect heteroscedasticity. So this is the end of the lecture. I hope you all found it useful. So let's kindly subscribe, and thanks for your time.